Hey everybody, I'm back here. This example, we're simplifying a trigonometric expression. And this is one of the techniques that we're going to be using when we try to verify a trig identity. And so this is sort of the lead up to what we're going to do next. And these trig identities will get more and more complicated as we go, and we'll talk about the strategies that we would use to verify these trig identities. So this is one of the strategies that we're going to use, and that's rewriting the expression in terms of sine and cosine. This is also going to help us practice finding common denominators when those denominators consist of trigonometric functions and complex fractions, all that good stuff. Great algebraic practice. And this is stuff that this is algebra that you're going to need in calculus if you're going to be successful. So this says rewrite the given expression in terms of sine and cosine and simplify. So cotangent is cosine over sine. Tangent is sine over cosine. Now I just say sine and cosine and sine, but there's always something inside my trig functions. In this case, there's always an x inside my trig function, but there always has to be something inside a trig function. I don't want you just writing cosine over sine. That doesn't even mean anything, and I will take off points if there's nothing there. It'd be like writing a square root and just leaving the underneath empty. There's something about this that is very unsettling until I put something inside, and then I feel a little bit better. So don't just write your trig functions without anything inside them. Not that I've seen this happen yet, but I just want to make sure that that doesn't happen. It's common to happen during this part of the course because we are writing these trig functions over and over again, and sometimes we get a little lazy, and I understand that, but just don't, okay? And then cosecant is 1 over sine, and secant is 1 over cosine. So I can actually just write this as one fraction. Okay. Now, the next step is to find a common denominator for all three fractions. Now, common denominators cannot be any smaller than the biggest denominator that's out there. So the biggest denominator out here is sine of x minus cosine of x. That is our big denominator, is this one right here. Okay? And we can't choose anything that's smaller than that. So I can't use sine, I can't use cosine. It would have to be something that's a multiple of sine, cosine, and sine x times cosine x. And since sine of x times cosine of x is a multiple of sine of x and cosine of x, my common denominator is just going to be sine of x times cosine of x. Now, what would I have to multiply sine of x by to get the common denominator sine of x times cosine of x? Well, I'd have to multiply it by cosine of x, right? So that means I have to multiply the numerator by cosine of x as well, because I'm really multiplying by 1 to find this common denominator here. There's the common denominator, so I have to multiply cosine by a cosine, and that gives me cosine squared of x. Now to get from my denominator of cosine to the common denominator of sine x cosine x, I have to multiply by sine of x. And if I'm multiplying by sine of x, I have to do it in the numerator and denominator. And so in the numerator, I have sine squared of x. In the denominator, I have our common denominator, which, if I'm writing fractions, right? If I have 1/2 plus 1/3 plus 1/6, and I chose 6 as my common denominator, which makes sense. I'd multiply this by 3. I'd multiply this by 2 over 2, and I'd multiply this by nothing, or 1 over 1. And so notice I can keep the same denominator, and I get I actually get 6 over 6, which is 1. 1/2 plus 1/3 plus 1/6 is 1. Pretty cool, huh? So we're doing the same thing here. So to multiply, I didn't have to multiply this by anything to get the common denominator. It was already there, so we're just going to have a 1 here. So now, looking at the numerator, this right here is one of our Pythagorean identities. Cosine squared x plus sine squared x equals, I heard you, you said 1. And so this is, this is 1 plus, this is 1 right here. This whole thing is 1, plus another 1 gives me 2 over sine x cosine x. All right, we did it. So let's take a look at an equation that's not an identity. So an identity is an equation where both sides are equal, okay? We want to prove that these two sides are not the same. So we're going to start with our trig identity sort of plan book. And the plans that we have, the way that we can execute this are systematic way of destroying these identities is to work on each side separately and try to get them to look the same, okay? So if I multiply out the left side of this equation here, what I'm going to end up with is, remember, if I have something of the form a minus b squared, that's a squared minus ab plus b squared. Sorry, 2ab. And so this is going to be sine squared x minus 2 sine x cosine x plus cosine squared x. So that's the left side. This is the left side of the equation. Okay? The right side of the equation is sine squared x minus cosine squared x. Okay? Now, this and this add together to give me 1. So I have 1 minus 2 sine x cosine x. And over here, I just have sine squared x minus cosine squared x, which I can write, since I know that sine squared x plus cosine squared x equals 1. I just use that up here to get this 1. Since I know that is true, that means I can rewrite cosine squared x as 1 minus sine squared x. And I don't know that that's going to help me, but maybe it will. So if I rewrite this cosine squared x as a 1 minus sine squared x, I get sine squared x minus a negative sine squared x, which is 2 sine squared x. And then I have this minus 1. Now these don't look equal. Can I turn a cosine into a sine to make this a sine squared? No, I can't. Also, it's off by a negative, right? I don't have 1 minus, I have something minus 1. And so these are not equal. There's nothing else I can do in this case. And so I've just proven that this is not an identity. So I will see you in the next video, and we'll talk about how to verify identities. This is the only example that we'll ever have that is not actually going to work. I just wanted to show you what it looks like if it doesn't work. We get to the end, and we don't have matching expressions. And there's no way to get this cosine to turn into a sine. There's no identity for that. And so we're stuck.